The first progression of our Capstone project is the early aircraft development. Here, before starting our aircraft, we consider for the consideration of design requirement, we construct period diagram and then design requirement, then construct analysis and last initial mass estimation. The first progression of our Capstone project is the design requirement. Here, our project goal is to make a medium firefighting seaplane that can deliver a considerable amount of payload, same performance like the existing firefighting aircraft. So we construct a payload range diagram. Payload range diagram is very important for the firefighting seaplane because it is firefighting aircraft performance is designed by the amount of water payload that can be delivered to the wildfire and fire area. Therefore, payload is really important in the project in the design requirement. Therefore, we make a payload range diagram of those existing firefighting aircraft and amphibious seaplane, and we set our design requirement for the medium size around those firefighting aircraft to get the performance around those aircraft. So after construction the payload range diagram, the next progress is setting the design requirement. For the design requirement, we set the entry into service around 2035, and our payload and range is acquired from the payload range diagram. Cruise speed, cruise altitude, max speed, and stall speed rail climb are similar to those existing firefighting aircraft, seaplane, and amphibious plane. So about the takeoff capability, because we will enter the service by 2035, we decided to make like VTOL with our fashion, our aircraft fashion both vertical takeoff and landing, and also short takeoff and landing from the water. So this is our design requirement. After design requirement, our next progression is the constraint analysis of our aircraft. Constraint analysis is important because these if we don't get enough wind area and track, our aircraft will not be able to fly. So we need to do constraint analysis. In the constraint analysis, we get equation from the general aviation aircraft textbook and from our lectures book. We will constrain our design by stall speed, landing, takeoff distance, cruise speed, max speed, ceiling, service ceiling, and rail climb. So, and from the constraint analysis, our parameter get power to weight ratio around 0.0824 horsepower by pound, and our wind loading around 40 power per foot square. After constraint analysis, we first estimate our initial mass of our aircraft by using the textbook Aircraft Design and Performance by Dr. John D. Anderson-Burke. So by using those method and iteration process, we got our maximum takeoff mass around 6,320 kg of the anti-mass 2,848. For the fuel mass, we calculate by Brugge weight equation of our design requirement is 1,300 km. So for that range, we got our fuel mass around 903 kg. For the research fuel mass, we also use range equation for 100 km to divert around the aircraft and 30 minutes endurance to land in the alternate airspeed. So this is the end of our early aircraft development, and for the future aircraft development, we have wing platform selection of our seaplane, tail design, CG calculation and mass breakdown of our seaplane, and then water tank design. After that, we will try to make a get off our seaplane in the open VSP. Then after that, finally, we will make a 3D and advanced sketch in our seaplane. So this is the end of my part, and my friend will tell about the propulsion system, development, and progression to use in our aircraft. Thank you.
From now on, I would like to talk about the design requirement for our propulsion system. As we already know, our aircraft is a medium area firefighting aircraft with a high payload capacity. So we have to consider the propulsion system that can operate effectively in various wildfire terrain and scenario, and also need to add the VTOL application too. So in order to require these propulsion requirements, we need balance power, endurance, and efficiency. To achieve these desired requirements, we have to do some technology options exploration. So as you can see, we have three types of propulsion system, which are conventional, fully electric, and hybrid. So as for the conventional, it is very reliable and mature technology, but it has very high fuel consumption and emission, which is not aligned with our goals. And for the fully electric case, we are not the unmanned aircraft, which leads to the requiring of larger energy density and longer recharge time is also not appropriate. So it's straight down to the last one, which is the hybrid propulsion system. It has integrated with both improved fuel efficiency and operational flexibility. We can combine with fuel and electric propulsion benefits to reach our goals. So for the final design choice, we chose the series hybrids instead of parallel hybrids. So why do we choose series hybrid? Because it has fewer driven generator power that is directly power to the motor, and motor straight go to the propellers. And we can able to use the battery that will be needed for our VTOL operation that has a very high power demand phases. And of course, it has easier integration with 2035 aviation technologies. So the reason why we don't choose parallel hybrid is simple, because it's need larger space, heavy battery size, and due to its increased weight, which will lead up to the much higher and much larger aviations, and we want to get more efficient aviation. So right now for the current progress, we have already determined what type of propulsion system we're gonna use. So we are now working on the power requirements for each flight phases using the equations from the books. And that includes like transition, cruise, loiter, and landing, and also the power calculation for VTOL configuration. So why do we need is because we need those power to use in simulations. So it will, by calculating these power requirements, we will get the much more accurate modeling of propulsion and energy usage of our system.
Okay, now let's have a look at our series hybrid JSON file, which show all of the parameters of our aircraft, like the propulsions, architecture, and this is a generator sections, which have several features, and also the electric, which show the required power demands for our aircraft for each legs, like takeoff power, cruise climb power, etc. And finally, we show some profile parameters like the cruise climb rate and the retransition durations and taxi and taxi out, etc. And also our maximum takeoff mass and the escaping distance, etc. So it's time to look at the propulsions. A quick look. We're now creating the series hybrid propulsions in the original toolkit, which is another new propulsion categories. We are now creating many methods to run in the simulation smoothly with the pre-existing codes to make it modular. So we have various concept here to how to use a propellant in the simulations and how the simulations consumptions is validated, etc. So it's just some progress right now. So for example, here you can see the wildfire spreading on a Pyrenees mountain front, and the aircraft are trying to suppress the wildfire according to the simulations guidelines and concepts, and then we see it's successfully terminated. Similarly, we run the simulations on other places. Here we are seeing the Salamis Island, Greece, and the response time is 2 hours, and our firefighting aircraft are trying to suppress it. And the last scenario you will see here is Palisades in California. There's a wildfire ignition in the center, and our firefighting aircraft are trying to make an indirect attack, which literally make a fire break line around the fire and trying to contain the fire instead of directly throwing the water on the fire.